prove that the group of order 2 is always cyclic. We know that the number of elements in a group is called order. So a group of order 2 is generated with two elements. One is the identity element E and another element is A. If the group is cyclic, it should satisfy the condition G equal to A comma A square is equal to E. A group constructed by a single element is called a cyclic group. Here the single element is A. With the help of the single element, we have to construct this group. If the given group G equal to E comma A satisfies this condition, then the group is called cyclic. For that, multiply the elements of group 1 by A. Is A into E comma A square, because A into A is A square. We know that any element is multiplied by the identity element, we can get the same element. So A into E equal to A, then A square. Then the product A square is also an element of this group G. Therefore, we may say the value of A square is either A or E. The value of A square is either A or B. So compare these two groups. A is the element present here. The product new element is A square. A square is also a member of this group G. Therefore, A square is either A or B. If A square is equal to A, take this condition. If A square is equal to A, then take this condition, A square is equal to A, multiply both sides by A inverse. A inverse A square is equal to A inverse A. A inverse A square is A power minus 1, A power 2. So A, this is equal to A inverse A is our identity element E. We have arrived at the condition of A equal to E. If A square is equal to A, then A equal to E. But in our consideration, A not equal to E. We expect A square is equal to E. Therefore, A square not equal to A. Then another one condition is the value of A square is E. See here, automatically we can write the value of A square is equal to E, because A square not equal to A. Since A not equal to E, we need A square is equal to E. Now the group is modified as G equal to the first element is A, take this group, and the second element is A square, then the value of A square is equal to E. Now we can construct a multiplication table with the help of these two elements, E and A. See here multiplication, E, A. E into E is E, E into A is A. Here A into E is A. Then A into A is A square. We already proved that the value of A square is equal to E. While constructing a multiplication table, a rule should be taken for our count. Both a row and a column should contain all the elements of a group. The given group is G equal to E comma A. See the first row which has the elements E and A. Now in the case of second row, A into E equal to A, then the value of A into A square is automatically E, because the second row should also hold both the elements. Then verify the column. The first column is having the elements E and A. The second column is also having the elements A and E. Therefore, the group of order 2 is always cyclic. All the cyclic groups are abelian in nature. This group is also abelian because the elements are subjected for commutation rule. A into E equal to E into A.